Around the world, many structures are being kept in service beyond their design lifetime. This means that deterioration of the structure, for example corrosion, may occur. In addition, the structure may be used and loaded in ways that it was not originally designed for. This can result in the actual service loads exceeding the design loads. Both deterioration of the structure and changes in service loads can lead to structural failure. To minimize the risk of failure and ensure the safety of users, structural health monitoring techniques have been developed over the past decades. Health monitoring of existing structures is important, as it can be used to prevent catastrophic failure and to manage the maintenance of the structure. When it is used to monitor new structures, such as offshore wind turbines, it can enable engineers to assess the remaining design lifetime, and in some cases the lifetime can be safely extended. This gives significant economic benefit. Hundreds of bridges and buildings are instrumented with health monitoring systems. State-of-the-art sensors are used to measure the dynamic response of the structure, such as accelerometers, strain sensors, and force cells that measure contact forces at the abutments. The ambient temperature and relative humidity are also measured, as changes in these conditions can affect the mechanical behavior of the structure. GPS data is used to track the motion of the structure and to synchronize different measurement systems. All of the information obtained from these different sensors is combined to assess the health of the structure. This is the process of structural health monitoring. In his PhD thesis, Kristof Maes developed a framework for health monitoring based on virtual sensing. Virtual sensing is needed when quantities of interest, such as the forces applied to a structure, cannot be measured directly. In his research, Kristof focused especially on identifying forces and estimating structural response using efficient filtering techniques. In some circumstances, it is very difficult or even impossible to directly measure the forces that are being applied to a structure. For example, what are the wind loads acting on a wind turbine, and what footfall loads are applied by pedestrians as they cross a footbridge? In his PhD, Kristof developed techniques that enable us to estimate these forces from a limited set of dynamic response measurements and a dynamic model of the structure.
On this footbridge in Ninove, I performed the validation of the force identification techniques I developed. Hammer loads have been applied at two given locations on the bridge deck. The acceleration and displacement response was measured using 3D acceleration sensors and optical displacement sensors. A detailed finite element model of the structure was built and represents the dynamic behavior of the footbridge. The model and sensor data were combined using the so-called joint input state estimation algorithm. In the development of this algorithm, I extended an algorithm that had been developed at the KU Leuven Electrical Engineering Department and first introduced in the field of structural dynamics as part of the PhD thesis of Elise Marie Laurens of the Civil Engineering Department of KU Leuven. For every time step, the algorithm estimates the forces applied to the structure and the corresponding system states in 3 consecutive steps. The algorithm does not only provide an efficient solution of the force identification problem, but also can be implemented in real time, enabling online monitoring of structures.
A significant part of the work performed within this PhD thesis concerns the design of a sensor network. Kristof investigated how many sensors are required to perform force identification and how the uncertainty on the estimated forces is affected by the choice of sensor network.
For the Ninove footbridge, we measured the response of the bridge deck at 12 different locations. By selecting different configurations of sensors, I was able to validate the proposed technique for sensor network design. In this case, uncertainty is introduced in the estimation by sensor noise, wind loads that are acting on the structure beside the applied hammer loads, and modeling errors.
Kristof demonstrated that the impact forces applied to the bridge deck at 2 locations can be reconstructed using only 2 displacement sensors and 2 acceleration sensors. As time proceeds, vibration data is fed into the algorithm and the forces are estimated in real time. A comparison of the applied and estimated forces shows good overall agreement. The oscillations of the estimated force right after the hammer impact are due to modeling errors. This demonstrates that an accurate model of the dynamic behavior of the structure is essential for force identification. The errors introduced by wind loading on the structure are small in this case, as the acceleration measurements coincide with the force applied to the structure.
The developed joint input state estimation algorithm can also be used to predict the response at locations that are not accessible for direct measurements. For this railway bridge, the main excitation consists of train loads and wind loads. The steel bridge is characterized by many sections where failure due to fatigue may occur. Direct measurements of the strains at all critical locations is very expensive and practically infeasible. In these circumstances, response estimation techniques can be used for virtual sensing of the strains at all locations of interest. The estimated strains can then be used in a fatigue assessment and provide an inexpensive alternative for predicting the remaining lifetime of the structure.
This approach for response estimation was validated using data obtained from a full-scale experiment on an offshore wind turbine mounted on a monopile. For these structures, the largest strain levels due to wind and wave loading are obtained below the water level, where direct strain measurements cannot be easily performed. The 3 megawatt wind turbine is instrumented with 10 microelectromechanical system accelerometers and 6 optical fiber strain gauges. A finite element model of the structure is used to extrapolate the response to unmeasured locations. In this validation case, the response was estimated at the lowest measurement level, 19 meters above the water level. Very promising results are obtained for this validation case. A comparison of the measured and estimated strains shows very good agreement.
As shown in this validation study, the response estimation techniques can be used for continuous monitoring and fatigue assessment of structures. The number of sensors required using this technique is small compared to the number of sensors required for classical health monitoring techniques, making this an efficient and inexpensive monitoring implementation.
In summary, within his PhD research, Kristof has developed a framework for virtual sensing that can be applied to a wide variety of civil engineering structures. These computationally efficient methods offer new opportunities for health monitoring and fatigue assessment of bridges, wind turbines, and offshore structures. The results obtained within the framework of his thesis have been acknowledged as important contributions to this field, as is exemplified by multiple publications in internationally reviewed journals.